Well, hello everyone, and thank you for being here today. We are super excited to be here with you and to have us with you for the next hour. So let's jump right in. So over the past few weeks, me and this guy basically created a small trading card game. And it's basically a bunch of collectible cards, like featuring unique characters as heroes. And I said game, but it hasn't been really thought to be a real game. It's more like a collection of cards where each card will showcase an interesting feature in Unity. So what we're going to show today is a short booster opening sequence, and then try to reveal the card one by one we designed specifically for the occasion. Sorry. Here's how we plan to spend our time. We'll start by showing the full sequence directly in the editor. After that, we'll have a simple breakdown on the foundation most of the cards share. And then we'll try to dissect every card by focusing on how several effects are made, such as holographic effect, portal, visual effect, shading, etc., all that stuff. In this talk, we will try to cover what we think is the most valuable and the most interesting to you. But if there's something you want to know, keep it in mind, and we'll try to take a few questions at the end. And also, the project that we are showing here will be released later. So if you want to take a look yourself later, if you are too shy to ask a question, it's fine. You would be able to take a look after. So before we get started, here's who we are. We're super lucky to have Orson with us right here. He comes from the video game industry. He's in the VFX team at Unity, and he specializes in visual effects, of course, and shadow graph. And I'm Remy. I'm more focused on environment and rendering because I come from the SRP team. But enough about us. Let's show you the shiny stuff because that's why you're here. Maybe switch. There we go. So we are live directly in editor. This project is using Universal Render Pipeline, so that you know. And basically what we have here is a few boosters on the left, and we can select and drag a few boosters, as you can see. The goal is going to be to drop the booster onto a landing socket to open it. So that's what we should do. Are you satisfied with this booster, Orson? Or maybe you want, maybe the middle one, maybe this one's better.
Let's go for this one.
Okay, are you ready? Okay, let's drop it, Orson. Ooh. As you can see, yes. Thank you. As you can see, we didn't lie. It's the shiny stuff. Maybe we can reveal the first card. Are you ready for that?
Yeah, let's go.
Okay. So it's a robot. So before we start, let's play a little game. Show of hands. How many of you remember this guy? Okay, a few people. I was scared. And for those who raised their hand, how many of you remember the name of this guy? Really? No one? Kyle, nice one, good. So it's super old, like older than us at Unity. It's been released like 13 years ago or something. It's been released with Unity 4, but it's still standing strong, as you can see. But now, I'm sure many of you are dying to know how the cards are made. So, shall we, Orson?
Yes, let's go. So for this project, as Remy was saying, like each card was built differently. And there was thoughts basically to highlight different visual techniques and features. But before diving into what's make each of them unique, let's see what's common between them. First thing is, of course, we wanted them to look good, but even more importantly, we wanted them to feel good, right? And this is why we've added some visual element and feedback so that even some simple interaction like hovering the mouse on a card like this just feels satisfying, right? So talking about those visual elements, one of them is this holographic shader on the back of the card. And actually, we're going to take a closer look at it. Right. So for those who don't know, iridescence is just an optical phenomenon where a surface appears to change color based on the viewing angle or the angle of illumination. And mostly this is due to a thin layer with some micro variation thickness that is disturbing the light reflection. And I'm pretty sure you already saw that on either old film like soap bubbles or, of course, trading cards. So let's jump and see how the shader has been built. So I'm gonna add it, and the first ingredient in this recipe is over here. It's the view vector. The view vector is just a vector that is going from the fragment position to the camera position. And here, what I'm doing is a dot product between this vector and an exposed one, which allows us to get this mask effect, which is based on view angle. Now, we can refine this mask by taking the sign out of it to make it repeat. And of course, we can add some parameters to make it tile and offset it. Now, for to replicate the variation in thickness, I'm just using a simple noise over here. And instead of taking it as is, I'm again taking the sign over here. This gives us this very like trippy or psychological pattern, right? That can be often seen on soap bubbles. Now, with this, we can add back our swipe mask effect based on the view angle. And by doing a saturate over it, we can now like sample a color gradient. And with this, we have a foundation, right, for a color shifting effect based on the view angle. Now, to get the metallic reflection, what we can do is take another noise. This time I'm using Voronoi cells, and the cells are animated, as you can see, based on the view angle. I'm adding that back to the swiping mask effect, and we can, of course, multiply that by a mask over here, and this allows us to get those reflection not on the whole card, but where we choose to. And again, we can, I think it's right here, we can just sample, again, a color ramp to get this color. We have everything that we needed, and finally we can blend everything together to get this, I think, pretty neat yet simple effect. And I think it's a good example of how you can just add more life to your object so that the interaction feels more satisfying, but directly into the shader without any C#. And this is how it's looking with a lit shader. Now that we've seen the back of the card, let's flip it. So I'm going to get back to the other scene. Discard this. Sorry for sniffing. And yeah, let's talk about what's composed the front of the card. So for this, we really wanted that each card acts as a small window, right? A portal to another dimension. And for this and either composition, each card was composed of several layers. So let's see them. The first layers, as we can see here, that display also some color shifting, is the border, of course. Then we take a background layer that is only visible inside the card frame, right? And that displays some parallax effect. Next come the subject. Each subject can be also composed of several layers. We'll see that a little bit later. We're adding a title on top of everything to reinforce the depth impression, a card coast on the top corner, and finally a VFX layer to really bring the card to life. So this is really what we wanted, right? To create some kind of miniature diorama, right? Where each layer can be either visible inside or outside the card frame. And for this, let me switch to this, right? It is, yeah. And for this, there is several techniques in Unity. We're going to show several of them with the different card. And for the first card, we choose what I think is the simplest method in Unity is just to rely on sprite renderer and sprite mask. With this, you have access to the mask interaction that allow you to choose if it's visible inside or outside the card frame. With this, you can create very cool effects, like the robot that is trying to escape the card by just setting some sprites to be visible inside the mask or outside. When your setup is done, getting the parallax effect is very easy. You just have to offset on the Z position, and you get very nice parallax effect based on the the tilting of your card. Finally, regarding the VFX, we've been using VFX graph to make them. It's a tool that gives you, I think, a lot of creative freedom. And for this, we just use one VFX with several systems inside it. And the cool thing is you have dedicated shape gizmos, so you can very finely end place each of your effects as you want. And finally, as you may have noticed on the previous slide, actually, by default, sadly, the particle from VFX doesn't interact with the sprite mask. So we had to be a little bit creative for that. And for this, we just use a render texture trick. So the idea was to take a secondary camera, right, that will render only the card mask over here and render it into a render texture. And this allows us to sample it into shadow graph to basically just clip what's not needed and what needs to be seen only inside the card. But I think you're going to be talking a little bit more about this technique.
Yes, and stay tuned for that. All right, I think we probably know everything about Robot Kyle now. Maybe it's time to take a look at the new card. Are you ready for that? Okay. You can switch the project. So I won't play guess the name for this one because first, it doesn't have a name. And secondly, I'm sure everyone has seen the Time Ghost video from last year. So this is what we have here. For this card, we wanted to go further into several key points. The first one is to making it more alive and dynamic. And the second one is to increase the depth effect compared to Robot Kyle. And one way to achieve that is to have more objects crossing the boundary of the card, like the portals that Orson was talking about earlier. So let's start by maybe looking how the masking is handled. And you can switch. So basically, Orson showed us the sprite mask technique, and it works great, but it's not really suitable for a more complex setup that we have here. The first reason is that the sprite mask uses sprites, and sprites are mostly transparent, and that creates some sort of issue with depth and sorting, basically. And it also forces us to create multiple planes and to split objects. For example, Robot Kyle is split into two. There is one layer that is in front and one layer that is clipped inside. So that was not really possible with a more complex composition. So basically what we did is iterate on the render texture trick that Orson just showed us. So it's basically a second camera that is rendering the same mask. But since we have to know now if the object is in front of the card or inside the card, we basically have to know where the boundary of the card is. So what we did is simply increase the size of this card mask, as you can see on the little animation. And then in the red channel, there was nothing on the render texture. So we basically store the depth of the card plane. As you can see, when the card is in front, is a bit brighter. That means it's closer, so the depth is stored properly. And it's the same when it's behind, the depth gets darker. And then basically what we can do is sample this depth directly into the shadow graph. And it's a simple comparison. Like you compare the depth of the pixel of the character and the depth that is stored inside the render texture. If it's in front, if it's greater, that means the object is in front. So basically we display it normally. And if it's below, we basically clip it inside the blue mask exactly as we did for the VFX layer. So now let's move on to the card. So as I said earlier, our goal was to increase the 3D effect of the card without the cost of rendering complex 3D geometry. Because I don't know if you remember, but Time Ghost has been made on HDRP, and it's a lot of vertices. There is the hair shader, there is complex stuff. And here we are on URP, and we really can't afford that. So basically what we did is use a stack of 2D plane, as you can see on the little animation. Here, there is three different things. There is the character that uses subdivided quads for vertex displacement. There is the environment behind that's using mostly parallax occlusion mapping on just simple quads with 4 vertices. And there is, of course, VFX for smokes and mirror. So for those who don't know, vertex displacement is just basically pushing the vertices on subdivided geometry. In this example, we're pushing the vertices of a plane using the height map shown in the middle. And Those maps have been rendered in another project, like using the time ghost asset from the asset store directly. There's nothing fancy in there. And all three different planes have their vertices pushed. And as you can see on the animation, especially when you tilt the card, it really helps like enhance this volume effect that we are going for. And in addition, since we split the object into different planes, what we did is slightly offset each plane in front of the previous one to increase the parallax effect. Talking about the parallax, let's have a look at parallax occlusion mapping, because that's what's mostly is using the environment. So for those who don't know, parallax effect is basically shifting the texture coordinate based on the view camera to create the illusion of depth on flat geometry. So similarly to the vertex displacement technique, it takes a height map as an input, and it also takes an amplitude. In Unity, there is a nice shadow graph node that's called parallax occlusion mapping that basically takes this into input. And with a simple like remarching algorithm, it will try to look into the height map step by step to basically figure out where the surface is based on the view camera. So when you move the camera, basically the UVs are changing, and that makes you think the object is actually 3D. And so this node simply outputs a new set of UV coordinate that you can use then to sample a base color in our case. So this is what we have for environment. So parallax occlusion mapping can be used like twofold here. The first one is to create the illusion of depth, as you can see on the small animation. And the second one is by modulating the amplitude a little bit with noise, you can basically fake movement. So here in the environment, it's basically divided into 3 different parts. There is 2 planes with a layer of width. There is one in front of the character and one below to basically better integrate the character and to increase the depth effect of the card. And basically by modulating, by multiplying the amplitude by the scrolling noise that you see here, we basically fake that the depth is moving back and forth, and that creates this little wiggle effect in the plane of width. But it's still just a simple plane with 4 quads. So to summarize, here, like both methods have pros and cons. Here it's really a matter of what looks good in your project and what you can afford, because they all have different advantages and disadvantages. Usually, like we more use vertex displacement for coarse displacement to avoid having too many vertices on screen, and use parallax occlusion mapping for finer details. But to be fair, every combination is actually possible. And now I'm sure you noticed that we didn't talk about the ghost and the VFX effect. It's not that we forgot about it, it's just we saved the best for last. So I can leave you with Arsene with that?
Yes. Thank you, Remy. So in Unity 6.1, there is custom HLSL in VFX Graph Run, right? And now it supports read-write graphic buffer and texture as input parameters. So basically, this means that VFX can now write into custom buffer and texture without relying on any global binding. So I'll be talking about read-write texture usage inside VFX, which I think unlock a lot of possibilities. And that also means that there is no C# needed anymore. With this, we can think of many things, right? We can think of fluid-like simulation like this one, but also like many, maybe like driving meshes thanks to vertex animation texture that will be written at runtime by particle in VFX. We can use render texture as buffer to store particle data, right? Or to use the texture as interface to communicate either with a shader or to make communication between 2 different VFX. And we can go beyond, like with particle simulation, animated texture, like the possibilities are endless. So before talking about this fluid-like simulation, I'm going to show you a scene, actually, that I've prepared for you. And we're going to try to see how it is to work with this inside VFX Graph. So basically, the setup is the same for all of the different examples that you can see over here. The idea is we have one VFX, and underneath it is just a regular plane, right? Like so. That is having a non-lead shader that is itself having a render texture. So here, what I want to say is that VFX is going to be used to write to those render texture that are going to be small or big, right? But we don't use VFX to render particles. Just we're using the simulation and we're going to write to the texture. But let's dive into this example over here, which is the simplest one. So here, what can we see? One VFX graph, which is composed of one particle, right? Pretty simple. And this particle is just this white dot over here. In the update context, what we're going to do, the update context is running every frame for every particle. So in this case, one particle. And every frame, we're going to write a particle color, which is here, the green, to a texel, right? And this is done thanks to the HLSL code here that I've been opening. And as you can see, it's very simple, right? I'm just referencing a texture, a read-write texture over here, some coordinates. And by using those coordinates here, I'm just setting the texel color with my particle color over here. This means that if I'm changing the color here, I'm changing the color that is written on the texture. And if I'm changing the coordinates over here, I'm writing to a different texel. But this is not really what we want to do, right? What I want is to be able to write to the underlying texel. So we need to convert our particle position to texel or grid coordinate. So this can be done in two ways. You can, of course, create your own custom HLSL function, your small library, and just use includes. I've been doing that for other examples, but you inside VFX graph, right? So you can use subgraph to do that. And this is what I've been doing over here. The logic, I won't show it to you because it's very simple, actually. It's just like I'm taking the particle position, remapping it into 0, 1, thanks to the bounds of our texture over here, and multiplying that by the texture dimension, which is here a 4x4 pixel. And here we have it. Basically, we can write to the underlying texel. All right, so this is great. Let's build upon that in the next example. Let me hide this. So the other example is roughly the same, right? But we have two systems. One system is, again, the same, writing to the render texture. And there is another system over here, which is composed of one particle per texel. So in this example, 16. Those particles are just laid down into a grid, and they're the one that I'm playing with. And they are just displaying some debug information, the linear index and the grid coordinate, right? All right, now that we have one particle per texel, this means that each particle can iterate on a dedicated texel, right? And for we're going to use this to our advantage, basically to fade our texture. This is what this piece of code is doing. Let me open it. It's relatively simple again. To fade the texture to what we're doing here is a simple loop between the current texel color and 0, thanks to a fade factor, right? So over time, now, the texture is being faded, right? So you can start to see a kind of trail effect that I'm building right here. So one system is writing to the render texture, and the other one is fading the texel. All right, so there is not a lot of resolution in this example. So what we can do is take our render texture over here and just maybe increase the resolution. What you can do also is to change the filter mode to bilinear. This way, you can average the color position, and you get a result that is starting to look decent. And as it's working with one particle, of course, it can work with several particles. So in this example, it's exactly the same logic, but instead of just one particle writing to the underlying texel, it's several particles, right, that are writing to the underlying texel. So it's all live. You can do whatever simulation that you want, change the color and everything. All right, this is great, but as you can see also, like even with an increased texture resolution, the results are still pixelated. And this is because like we're just writing to one texel per particle, right? So what we want to do is, how to say that, maybe create a kind of brush for each of our particle, right? And for this, there is many different ways of doing it, but there is an example, of course, for that. We're going to create a sphere mask, right? So in this example, we have the same, one system, one particle per texel that are going to be like iterating on each texel. And what we're doing here is the following. Let me zoom a bit. So the particles are represented by those green dots over here. And what I'm doing is I'm computing the distance between those texel position and the blue dots over here. By doing so, dividing that by a radius that you can see over here, you can get a kind of sphere mask over here. And let me show the code, because again, it's not that complicated. Over here, so we still have the fade, right? And here is the sphere mask over here. It's just the distance between the particle position and the blue dot position divided by the radius, you get your sphere mask. And something that is different also here is instead of overwriting the texel color, I'm doing a max operation. So here we have kind of the previous texel color results, and this is our sphere mask. So we're doing a max between the two, and this allows us to get this pretty neat like kind of trailing effect, like so. And now I can play with the radius over here, and it's starting to get fun, right? But here, it's just like a simple constant radius value. And you are inside VFX graph, so this means that you have access to the full set of nodes, right? You have access to the full library of VFX graph. So instead of taking just a constant value for this sphere mask, what I can do is just add some noise to it. And maybe we can just animate the noise. I don't know, we can play on the frequency, and maybe we can increase the size of our radius, like so. And now we're starting to get very interesting results, like so. But this is just with one position, right? So let's build upon that and see how we can do that with several position, basically position array. And for this, again, the answer is texture, right? So in this example, I'm having another simulation, which are the red dots over here. So it's a simple simulation, just some turbulences, right? And they're warping. But now, each frame, the particle that you can see over here, are writing their position and size into a small texture. So in this case, we're using a texture as buffer, right? And we can take a look at it. It's a very small particle, 64 by 1, which allows us to store 64 position. And this is great because this allows us to make different VFX systems communicate between each other by knowing the position of different particles. And this is what doing the second system over here. Basically, the second system here is the same as the one that we've seen earlier, but instead of doing the sphere mask on one position, there is a for loop here that is iterating on all the position in our array. And again, we can add some noise to our radius and start to get very like interesting and intriguing results to create this kind of mushroom-like simulation. I think we have most of the brick that were needed to better understand the fluid-like simulation of the time ghost card. So yeah, let's jump to the next and final example, which is this one. So here, as we've seen earlier, it's the same concept, one particle per texel to iterate on every texel, right? And we've seen that all of those particles, we can convert their position into grid coordinates, basically into UVs, right? This means that we can also sample other texture. And this is what I'm doing over here. In this example, I'm sampling this texture, and every frame, I'm adding a bit of this texture. I'm accumulating it a bit every frame to the render texture. And while we're doing that, we're also fading the texture. So it's a balance between the two. But now that we have that, excuse me, well, we can also distort the UV, right? You can change the UV to get more interesting results, as we have seen before with the computation of our distance. And this is what I'm doing over here. So as you will do it in in a regular shader, what you can do is distort the UV. So here I'm just doing like a simple like UV offset, right? And over time, we can see this kind of nice diffusion effect that is happening. So you can think of using these to like scale the UVs to get a kind of blur effect, or you can offset it on the left and right. And I think you can start to see where I'm going with this. You can, of course, add some noise using VFX Graph library. And now you got it. You're just messing around with the UVs, and you can just play with it. It's really fun, actually. And you can get very, very interesting results, right? And now that we have this, we can, of course, build upon that and maybe, again, use all the VFX node library to get even more details. So in this case, what I've been trying here is just mess around with the fade factor over here to basically create this kind of flame-like pattern. So we can maybe increase the roughness out of it. We can change the tiling. I mean, after that, it's just you messing around with everything. And yes, I think we've seen everything. For the time ghost card, it's the same. Exactly the same system, just instead of using the Unity logo as texture, I'm using the time ghost soldier texture over here, and it's using to do the advection and the diffusion, and I'm also using a small mask to better control where I want my distortion to happen, right? So this is a simple like shader distortion, and this is what it's giving us over time. So this is the end for this. I didn't talk about performances, but sadly I cannot do the small debugger on Mac. But the performances are pretty great, actually. I think it was 0.2 millisecond on a like a mid-range GPU, and on the rendering side of it, I mean, it's just an unlit quad, right? So it's really, really cheap. So yeah, what I wanted to show you here is we really can think of VFX Graph as a compute shader like sandbox, right? Where you can use all VFX Graph node library and play with that and play with the texture. But yeah.
Cool.
That's it.
Thank you, Arthur. That was a lot to digest, but that was fascinating.
Oh,
yeah. So, who is ready for the next card? I'm guessing everyone. Okay, so maybe switch, and then we can reveal.
Like this.
Yep. So let's reveal the last one. Okay, so real 3D. Nice. So let's play the game again. How many of you remember this wonderful person? Really? Less than Kyle? She's younger. Come on. How many of you remember the name? Sarah? No, it's not Sarah. You're not close either. Really? No one? Don't be shy. Come on. Okay, it's Ellen. It's supposed to be Ellen. She was released like only 5 years ago with Unity 2020. She was released as a 3D game kit tutorial on Unity Learn. And yeah, with her, maybe let's focus on something lighter, like a little bit of Toon shading before diving again into rendering. You ready, Orson?
Yes. I'm just trying to wait what I've done. I guess something isn't. Yeah. So basically, what I wanted to do is just a very quick detour. Let me unmaximize this. Okay. Yeah, I just wanted to make a quick detour. It's going to be quick to talk about some of the new features and samples that have been landing in Shadowgraph. The first thing is the Shadowgraph template window. So for those of you who don't know, now in Shadowgraph, you have this new entry, which is called from template, right? And these basically allow you to don't start from scratch and to start from something that is meaningful, that is more representative of the final outcome. So if you want to make a sprite shader, instead of starting from scratch, you can now start with the starter templates. And this really accelerates your workflow. This template window can also be used actually to create your own custom templates. And custom templates are a great way maybe like to enforce technical guidelines into your team. Talking about those custom templates, here you can see some of them, which has landed in 6.3, if I'm correct, and that are all about custom lighting in Shadowgraph. So it's a sample that is available in the package manager that you can easily download. And with this, you can create your own custom lighting shader inside Shadowgraph. This is what we've been using for Ellen over here, that display a Toon shader, and this is just the starter template, actually. So it's really looking good. And what I wanted to show you here is that all of those templates has been made with subgraph, right? So you can really like take a look into them and dive into the different subgraph and take part of it to create your own custom lighting directly into Shadowgraph. So yeah, I think it's really cool to have this. So I encourage you to take a look. And that's it. Really quick.
Thank you for the quick detour, Orson. On my side, I wanted to focus a little bit on how we did the portal effect for Helen, because as you've probably seen, she's a different character, and she's using like real 3D compared to the other one. This time, we will try to use the URP render feature for that. And you're probably going to hate me for it, because each time we show a new way to make a portal, we destroy the last one with a bunch of limitation. That doesn't mean the previous methods were bad. That just means they were adapted to what we were doing. So the card mask approach with the render texture works great for Kyle and also for Time Ghost. But of course, it needs to have a second camera, even though it's not rendering a lot. It's not really advised to have multiple cameras for performance reasons. Of course, we need also to modify each Shadowgraph to be able to sample the render texture. So it can be tedious if you have multiple material in your object. And of course, it only works well when we can see the card mask. So when the card is flipped, then there will be all kind of problem. We didn't have those problems with Kyle and Time Ghost because they were plain. So when they are flipped, then we don't see anything because the normal is pointing the other way. But with Ellen, since it's real 3D, then we would have all kind of problem. So this is why we suggested to try a new method. And what I wanted to do is to basically try this new method directly in the editor with you. So let's move on the laptop again. Let's open the right scene. Here we go. Of course, Orson made a bunch of changes.
Sorry.
So here we go. Basically, here's the initial situation here. We have Ellen, we have the card border, we have the background in cyan. We also have a studio background in gray. And to help us, we have two super cool masks. The first one is what I call the card mask outside. It's just a simple shader with the masking technique, alpha clipped, in white. So it's everything outside the card. And there is the same in blue, which is everything inside the card. So I will hide them so that we can see it more clearer, but they're still there. So basically here, what we want to do is to confine everything like Helen and her background inside the card to make this portal effect. And as you can see, she's animated, and sometimes she moves her head in front of the card, and we still want to keep that because we want to keep this kind of portal effect exactly as you see here. So here on the right, I have a URP renderer that is actually used on this scene. And what we are going to start to do is to try to confine the background to the card first. And for that, we're going to use the stencil technique. So for those who don't know what a stencil is, it's relatively simple. It's just a screen space texture, a screen space buffer in which you can read and write. In URP, the stencil has only 4 bits available for users. So that means you can write anything from 0 to 15 into that texture. And it's way more than we need to do our effect. So let's first try to make it in 2 paths. Let's write something into the stencil, the inside of the card. And then let's read that stencil to render the card background. So let's first add a new render object path. Let's call it card inside stencil. There we go. We are doing everything before opaque to avoid interfering with the opaque path that goes after. We're going to select the right layer mask here. So card mask inside. So we have our blue mask that we've seen before. We don't want to override the material. And we are going to check the stencil feature. So here we want to write regardless of the content of the stencil. So we are going to choose always as a compare function. So when it passes, so always, we are going to replace the value here. So let's select replace. And we are going to write a value, an arbitrary value. So let's not put 0 because the stencil is already 0. So let's put something like 15. And so we can see something. We can also override the depth of this stencil and just force it to not write it so that it gets curled behind. So here, nothing has changed. Great. But I can assure you that we are actually writing into the stencil. Here we are on metal, so we can't really access the stencil, so I can't show you in the frame debugger, but I will still show you so that you can do it on Windows if you like. Basically, we have our path that's been written here. We can select stencil, and here, technically, we should have the stencil directly where the card is actually his. But metal doesn't allow that, so we can show it. But trust me, it's there. Now that we wrote the stencil, we can basically read it. So let's first start to remove the background from the opaque layer mask. So remove the background, and we can render it again. Let's call that card background. We are still before opaque. Let's select the right background. Here it is, back to square one. And what we're going to do here is to check the stencil feature. And here we don't want to write. So we don't really care about the pass fail and z fail value. We want to check something. So the compare function should be equal. And we want to render the background only when the stencil is equal to 15. So let's move to 15. So here we go. We have our nice stencil effect for the background. Now about Ellen. The problem is with Ellen, if we use the same technique, then her head will be clipped, of course, outside. So we can't really use this technique as well. What we're going to use is the other mask that showed you earlier, so the mask outside. And what we want for this mask is to kind of write the mask and write the depth of this mask, but do not write the color. Basically, like make a transparent mask outside the card so that everything behind gets curled because it writes its depth, but it does not obstruct the view because it does not write its color. And that's exactly what a depth-only shader is. So here, what we want to do is just create a new render object path here. Let's call that card outside mask. We are still before opaque. We want to select the right mask, so it's card mask outside. As you can see, it's rendered now. But what we want to do is to override this material with the depth only mask because we don't want to see it. We just wanted to write its depth. So let's select the material. So here, it's a material that we actually made. It's just a shader that you have to write by hand, sadly, currently in Unity. But to be fair, it's a super simple shader. As you can see here, it's just sampling a texture. And the only real information here is basically, oh, sorry, we're on Mac. So it's inverted. So it's only z write on to force to write its depth, and color mask 0 to force the color not to be written. And to be fair, that's about it. There is only 2 simple lines of code. So here, the legs are hidden, and as you can see, when the head is going to go over, it's going to be fine. But you still see some blue outside, and it's not the mesh that is actually rendering. It's just the background of the camera. As you can see, if I go back on the camera here, if I move the color, you can see that it's not the mesh, it's the background of the camera. And why is that? Is because now that we wrote the depth outside the card, everything behind gets curled because of the depth sorting thing. So what we need to do is to rewrite our background just before what we do to be able to have the background. So let's do that. So let's remove the background from the opaque layer mask, and this is going to be our last render object pass. Let's add the new render object pass. Let's call that real background, for example. Go. We are still before opaque, and we select the real background. So here we go. We are back to square one because we are still after. So instead of rendering before opaque, we can go on the event just above, so after different light. And here we go. We have our proper portal effect. The last thing that I wanted to do is Ellen is currently clipping against her background. So what we can do is go back onto the render pass that we just did for the background and override the depth here and force it to not write so that Ellen won't clip against it. And basically now we have our nice effect. We can move the background and Ellen is never clipped. We can even put it in front to have some super weird parallax effect. And what I want you to remember here is like in 10 minutes with only 4 underpasses and 2 simple lines of shader code, we are able to do a cool portal effect super quickly. So here, we need to go to the next slide. As a side note, it's nothing new what I just showed. Everything was already possible, like reading and writing the stencil in handwritten shader. It's more convenient to do it with European render passes because it allows you to do it without having much knowledge and without having to code anything. In a perfect world, we'd want to have those features into the shader graphs to be able to write multiple bits for multiple stencil if you want multiple cards, etc. And this is exactly what our shader graph team is working on. We can't really promise anything because it's not out yet, but hopefully in 6.5 or 6.6, we'll be able to have this feature directly. So watch out for the next release. So now, this presentation wouldn't really look serious if we didn't talk about performance a little, because we only showed 3 cards, so performance wasn't that big of a problem, of course. But in a real game scenario, of course, you'd have like at least 40 cards or 100 cards or something like that, and there's going to be problems. So what would be our option for that, to customize the material of the card if you have way more cards? So currently in Unity, you have already a few options. There is the material variant that you can create by hand. It's a bit tedious to make, but it's super useful. There is a material instance that you can create at runtime. It's great, but kinds of break batching as well. We also have the material property block. That is pretty great, but it's slow in performance. So all those methods works great, but they all have their kind of disadvantages. So for all these reasons, in 6.3, we introduced something we call the renderer shader user value, so RSUV. So what's behind this scary word? Simply put, it's basically for rendering, we have to allocate buffer to send information to the GPU. And so basically so that shader can actually render and make draw calls and stuff like that. So for efficiency, those buffer have a fixed size. And we realized that in one of those buffers, there were actually free space. So we basically took advantage of that and decided that we should reserve like a full unsigned int to pass data from the CPU to the GPU. So you can actually set this data using C# on a renderer, and every material on the renderer will be able to get this value. And then using a global variable on the shader graph or in handwritten shader, for example, you'd be able to retrieve this unsigned int and customize your material based on it. And what's super cool is that compared to the other method, since we are constantly updating this buffer anyway, it means it's basically free to send this data to the GPU. And in addition to that, like if you combine it with the GPU resident drawer that we showed last year, it doesn't break batching. So here I've set up a simple scene with a simpler shader. Basically, all cards have different properties, as you can see here. And next, what we need to decide is how to pack this 32-bit of data, because it's not a lot. And of course, you have to decide which property goes to where and on how many bits you need to do that. So let's use an example. Let's try to make this simple card here in blue with the orange border, with the text displayed, and the proper unite here, because we are in 2025. So I don't know where you stand on binary, so let's start easy. The display text is more or less a yes or no question. So let's write it on 1 bit. We want to display text, so let's write 1. The back color, it's basically choosing between 4 colors, so between red, blue, green, and black, as you've seen on the example. So that means you can pass an index between 0 and 3, and then sample something on the shadow graph, like a color palette, for example. So 2 bits is enough. Here, so as you can see, 4 possibilities. So let's pass 2, because we want the third color. We have the unite here. We want to pass 25, so that means we need at least 5 bits to pass this data. And we have the random color that is split between 3 channels of 8 bits, because 8 bits means 256 possibilities. So we want to pass orange, so let's max out the red. So 255 on the red, half in green, 128, and there is no blue in orange, so let's pass 0 for blue. So here, it looks tedious, and it would never been done by hand in a project. So what we've done at Unity is basically give you a sample function in the RSUV sample to basically encode and decode binary to be able to pass your data without having to worry about to do binary, because it's a hassle, to be fair. I won't go into details of the code, but it's basically encoding integer at a start index at a specific length. And we have the same kind of thing directly in HLSL. So basically, that means you can do that directly in your animation shader or in a custom node in the shader graph, and basically use those functions to retrieve the value instead of using the material inspector, for example. And here I want to talk a little bit about performance. So let's open the actual scene that I've just shown you. Let's use that. Here we go. So here we have the scene that I've just shown you. So there is the 40 card here. And I've set up a simple script here that is using either RSUV, so the method I just showed you, or material property block here. So as you can see, when I switch between the two, nothing visually changed because we are actually sending the same data, so that doesn't make sense. So let's start with the material property block. Let's have a quick look at the frame debugger here. Let's enable it. Here in the draw opaque pass, you can see that there is 121 draw calls. There is 1 for the background, and there's 120 draw calls for the card. So that means it's 3 draw calls per card. There is 1 for the card background. There is 1 per digit of the card. We want to run 25, so we have 2 digits. So as you can see, it's not really efficient. 120 draw calls for 40 cards is a lot. And here I've also set up rendering marker, which I call the CPU rendering time, which is basically the time the CPU takes to gather all the data to send it to the GPU so that shader can actually prepare draw calls. So here on Mac, using material property block, it's more or less 2.5 milliseconds. And when I switch to RSUV, you can see that the number dramatically drops. So it's basically 5 times faster. And here we are on Mac. On Windows, it's even larger. And if I go back to the frame debugger here, go. As you can see on the draw opaque object, there is only 3 now. It's not only 3 draw call, it's 3 batch. So it's not exactly the same, but it's way more efficient. And that means there is 1 draw call for the background, 1 draw call for the back of the card, and 1 draw call for the whole digits of the card. So here with RSUV, what I want you to remember is that it's just way more efficient to use this method compared to any other method that it's actually already in Unity. Of course, as you've seen, there is a small price to pay to set up this. You have to encode the value, you have to decode it. But once you pay this price, basically, it will allow you to reduce the number of variants that you have in your project. So it will make the project way more clean. And now that you've deferred every variable from the material inspector directly to the C# inspector, that means everything can be gameplay driven way more easily. And on top of that, you gain performance. So isn't that wonderful? What's not wonderful, though, is that we are arriving at the end of our talk. So let's recap a little bit what we've seen. We've seen multiple ways to create portal, the sprite mask technique with Kyle, the second camera render texture trick with Time Ghost, and the render feature for Ellen. We've seen how to add volumes to simple plane using like either vertex displacement or parallax effect, either by offsetting some plane or just using the parallax node directly into the shadow graph. We've seen how to add life to cards using distortion, of course, VFX, and holographic shader to add feel to your game. And of course, we've seen how to improve all of those three using the RSUV feature. So thank you for listening to the end. Thank you.